Good afternoon, everyone. My name is Wang. I'm from the Concrete Lab, the University of Tokyo. So today my presentation title is a numerical approach for estimating corrosion possibility of reinforcement concrete structure considering crack development. First, let's talk about something the research background. As we well know that the corrosion is the major stress of concrete structure. Take one simple beam, for example. So if the beam applied a load, the concrete will crack it, and the chloride ion will easily go inside the concrete material through the cracks and make the reinforcement corrosion. So generally, most current concrete cycle considering the chloride diffusion effects, for example, the Japanese design curve. But because we don't have a good measure to considering the two-layer material, the diffusion, chloride diffusion, so generally we use the concrete consider this ring, and we just adjust the parameter diffusion coefficient to consider the crack effects. But however, we know that this method is not so good because actually this diffusion process is the two-layer diffusion. One layer is the cracked concrete and second layer is uncracked concrete. So without the proper method of two-layer material, so we cannot assess the chloride diffusion of the cracked concrete layer, and also we cannot consider the interaction between the crack development and reinforcement corrosion. And also we cannot assess the long-term performance of the cracked concrete structures. Moreover, we know that actually in the U structure, every parameter is the uncertain and very random. For example, the diffusion coefficient, and we have the concrete cover depth and surface chloride content type dependency, something like this thing. So again, this background. So we propose a new design measure to considering these above parameter effects. First, we can do something like inserting eradication, and then we can get the parameter probability distribution. For example, we can know the concrete cover depth, and then we can use the diffusion, chloride diffusion model, and also the corrosion model, coupling with the Monte Carlo simulation that we can consider in the assess the corrosion possibility. And then based on the corrosion possibility, the engineer can design his structure. For example, we can choose what's the concrete mixture, or for example, what's the water bladder ratio, what kind of assets you want to use, how much thick the concrete depth, something like these things. Generally, this method is very easily understood. The most important thing is that typical thing is that if we want to use the Monte Carlo simulation, that means that if we want to get the corrosion result, we need to at least 1 million simple link. This means that we need a very highly efficient approach to considering the chloride diffusion, and especially right now we have for the cracked concrete such two-layer material. Actually, we already developed something the rapid numerical approach for the two-layer material, the diffusion chloride diffusion, and we already developed model this approach. I already presented this paper. This paper just accepted by the Journal of Structure and Infrastructure Engineering. And if you are interested, you can find our details from this paper. I suppose this paper will be online soon. And this approach generally is developed for the surface treated concrete because the surface treated concrete also has the two-layer material, or water repellent layer and normal concrete layer. And this approach can consider the diffusion process for the surface concrete material, surface treated concrete, and also assess the corrosion possibility of the surface treated concrete. Anyway, we generally simply introduce this approach, and in this numerical approach, we separate two different material, one layer material, second layer material. This two-layer material has a different diffusion coefficient, so we have the two different governing equation for the diffusion coefficient, the diffusion process. And because we also know the boundary condition, so we can set in the boundary condition for the chloride diffusion, something like these things. And because we can use, and then we can use the variable separation method to get the general solution for these two layer the diffusion process. And based on the boundary condition, we can simplify this more the solution, and the AN, BN, eta n, beta n just use the AM process. So this one is our general solution for the two-layer material chloride diffusion process. And this solution is a series solution. So the most important thing is that we need to determine the lambda n. For the lambda n, we can use this equation to determine. And how to determine this equation, we already also derived one very rapid numerical approach. Again, so if you want to, you are interested in this approach, you can find our paper. The paper presented the details, the math derivation, and the algorithm, and you can find them there. So anyway, we just said that this approach, and we can give you very convergent results. For example, we can consider the characteristic rules and the numbers, the steps, and also the intervals. So if we properly select this parameter, we can get the convergent results. And second thing is that this measure is related comparing with the final element measure. And we set up some several cases. In this case, we considering the time dependency of the diffusion coefficient, and also we considering the surface chloride content time dependence, and also we can assume just different diffusion types. So you can see that this approach get almost same result with the finite element method. So this result in conclusion, this approach is the convergent and reliable. So based on this approach, let's say that how to use this approach to consider the crack concrete. So we know that in the crack concrete, that first that the crack length will develop as time goes on. You can see that something like these things. Because the crack development, so if for the first layer, the diffusion coefficient will be increased, the linear increase because of the crack development. And in something the normal concrete and also all the uncracked concrete, the diffusion coefficient will decrease because of the continuous hydration. And also we consider the surface chloride because the surface chloride accumulate on the surface. So we also need to consider time dependence. Then use the step function to separate this linear process in several steps. Then each step has a constant value. Because these are constant values, so we can use our approach to considering these things. And also, we just also consider the chloride binding. And in this case, in this paper, we just simply assume the chloride binding ratio is a constant to simplify the calculation. And we are right now, this model is simple, but right now we improve the model. In the future, we will consider the linear chloride binding. And as we can calculate these things, for this case, we have to set up the several cases. We also consider different time dependency, and also we consider the surface chloride content. We also consider different time. And this one is the crack development. You can see that in this case, the crack development is very smooth, and then the cracked concrete, the diffusion coefficient is increase as the time goes on. The uncracked concrete, the diffusion coefficient decrease. So also this case, the crack development is not so smooth, the nice step functions, something like these things. But anyway, our approach also gives us a very good result comparing with the finite element method. And also, we also can consider in the different time, you can consider even we use 15 years, our approach gives us very good result comparing with the finite ending measure, so this measure is reliable. And most important things that we need to know the time cost. So for this case, we can see that because if we use the finite ending measure, and this measure need to consider in the diffusion process step by step. So usually we had 8,000 seconds, almost 1,000 seconds for one case. But if you use our worksheet, almost the case, we just need to exact point to 5 seconds of complete one case. So if we want to use the Monte Carlo simulation, for example, if we want to use the 1 million sample, let's consider 100 years. So let's assume that we use a simple network computer, we has 8 cores for the perimeter counting. Then if we use the finite ending method, that means that we almost use 200 years. That's almost impossible for the calculation. But if you use our approach, just 8 and 9 hours, so then we can complete the calculation. That means that we make this calculation become feasible for engineering applications. So right now we already developed this numerical approach. So let's use the one case study to see how the cracking effects, crack concrete. So this one is the U project is the Western Port in Shenzhen cities, and this West part actually we're doing something in situ irrigation, get the concrete color depth, the possibility distribution, something like these things. And based on this distribution, so we set a sensing parameter. For example, we consider the RT, the crackiness, and 10 millimeter, 20 meters. And also we consider in the chloride binding ratio, it's a 0.1, it's a 0.15, and also consider different diffusion type dependence for the diffusion coefficient. So you can see that actually if the diffusion, the corrosion possibility increase as the crackiness increase, and also the corrosion possibility will decrease if the chloride binding ratio decrease. So for this case, we can get that the actually crack development and the chloride binding is important to assess the long-term performance of the concrete structures. So let's make some conclusion. And this mod, we developed something the numerical approach. This numerical approach we can consider the cracked concrete, the diffusion, correct diffusion process, and we can get there for the case study. We know that crack development and the chloride binding cannot be ignored. But anyway, this model is really primary model, we are simple model. So our perspective and something we are doing, something that we are introducing the reinforcement corrosion model inside, and also we actually consider in the coupling effects of the reinforcement corrosion and crack development inside, and also we can consider in the chloride binding, for example, the linear chloride binding relationship inside, and most important things that we also going into improving the calculating efficiency. So our target is that we want to improve this measure. You can finish in the 4 hours. If better, we can finish 2 or 3 hours. Even use a simple computer, something laptop, something like that, so that the engineer can use the one for their concrete design. So we are doing something these things that. And if you are interested in this topic, we are very welcome you to welcome you to cooperate on this topic. And that's all. Thank you.